Okay, so now we get to the real workhorse of infinite series, which is the geometric series. And a geometric series is any series where the terms in the series can be written as a real number raised to an exponent, where the exponent is the index. And so we've actually seen one of these. We've been working with one of these. Um, this infinite series we looked at, where we summed from n equal to 0 to infinity of 1/2 to the nth power. Right? So you can see what happens. Every term, every successive term gets multiplied by this thing that we call r, this number r. So this is a geometric series where our r is equal to 1/2. So we're basically summing up successive powers of this base. And it's important to appreciate that a lot of infinite series are in fact geometric series, but they're kind of in disguise, okay? So let me show you one that's kind of like that. And what that's going to require us to do is that's going to require us to kind of re-index a little bit, okay? So let me show you what something that's a geometric series, but it's not so obvious in the beginning. So I'm going to take the sum from n equals 0 to infinity of minus 1 to the nth over 4n, 4 to the nth. And notice that this is not technically a geometric series because the r is going to change from term to term. Okay, we're going to have positive and negative terms that are going to alternate. And so if we just sketch out really quick what this is, right? This is 1 minus a fourth plus 1 over 4 squared, which is 16. I'll write it like this. Minus 1 over 4 cubed plus 1 over 4 to the fourth minus dot, dot, dot. And notice it does not have this form. However, what I can do is I can gather up the positive and the negative terms separately. So I'm going to gather up the positive terms here. And I can see what happens. Every time the next positive term is going to go up by a factor of 4 squared, right? I went from 4 squared to 4 to the fourth. That's going up by 4 squared because I'm skipping this term right here, okay? And I can also group together all of the negative terms. And the same thing is happening. I notice they're going up, or they're going down. They're being multiplied, right, by 1 over 4 squared, going from one term to the next term. And so what I'm going to do is I'm going to put the positive and negative terms separately. So this is going to be equal to, if I look at the positive terms, 1 plus 1 over 4 squared plus 1 over 4 to the fourth. And again, they're going up by a factor of 4 squared every time, right? 4 to the sixth plus 1 over 4 to the eighth, dot, dot, dot. So these are all the positive terms. Okay? And if I look at all the negative terms, right? I have 1/4 plus 1 over 4 cubed plus 1 over 4 to the fifth. I factored out the negative sign, right? 1 over 4 to the seventh, dot, dot, dot. And notice the way I want to write this. Really, to write a geometric series, I want to start at n equals to 0. That's really the form that we want, okay? So the first is already a geometric series. If I look at just the positive terms, right? The positive terms can be written as powers of 1 over 4 squared. Let's see, 2, 4, 6, right? So this is going to be, I'm sorry, this is to the first power, sorry. This is to the second power, okay? So this is 1 over 4 squared to the 0 power, 1 over 4 squared to the first power, 1 over 4 squared to the second power, and so on. So by splitting these terms apart, I'm going to have a geometric series for the positive terms, right? And I can do the same thing here. Notice I can factor out a 1/4. So this is minus 1/4. And this is going to be 1 plus. And notice I'm going to get exactly this series I had up here, right? When I factor this out, the first term is going to be 1. This is going to be 1 over 4 squared. This will be 1 over 4 to the 4th, which I can write like this, 1 over 4 squared squared. And you can convince yourself that you end up getting the same thing. So notice that these are the same series now. If you look at this carefully, you realize these are the same series. Oops. Let me go back here. So this series, this infinite series, and this infinite series are the same. So I can factor them out. And I'll end up getting 1 minus 1/4. When I factor the infinite series out of this term, I have 1 left over. When I factor out of this, I have 1/4. And then I have my infinite series here. Whoops. Keep on wanting to put a square there. Okay, dot, dot, dot. And so sometimes you have to do a little bit of manipulation. So this is something that you want to kind of make sure that you're good at. This is a little skill that's really useful. Okay. So one question we have is, well, what does this converge to? Okay. I mean, okay, we've expressed this in terms of a geometric series, right? Where r is 1 over 16, 1 over 4 squared. But still, what is the value of this? And the geometric series is unique in that it is one of the few infinite series that we can actually evaluate easily. So it turns out when we have a geometric series, and I want you to pay special attention here, when the index starts at 0, okay, and I have a geometric series, it equals 1 over 1 minus r. If the absolute value of my base here, r, is less than 1. And if the absolute value of the base is greater than or equal to 1, that's what otherwise means, right? This does not converge. All right. And you can kind of see why that's the case. I mean, if you take a number greater than 1 and raise it to a power and you keep on increasing the power, the reason why this is true is you're going to end up satisfying the test for non-convergence. Okay, so that's the issue here. Okay, and so let's go ahead and apply this. Okay, so we had this example that we looked at way back a long time ago, where we were taking the sum from n equals 0 to infinity of 1 over 2 to the nth power. And so this is going to be my r. And so this result tells us, well, this is equal to 1 over 1 minus r. And so I'm going to get 1 over a half, which is 2. And that's what we saw earlier. If you recall, when we plotted the sequence of partial sums for this infinite series, we saw them converging to 2. Okay, if we go back and we look at this example we just considered, where we had to reindex and kind of move around terms a little bit. This was our series, right? Hold on a second. Well, I can actually write this like this if I wanted to. Okay. And we saw that this was equal to 1 minus 1/4 times this infinite series. So I'm referring to this result we had right here, right? So this is 1 minus 1/4 part, right? And this is the infinite series. And this infinite series we said was a geometric series. And so it's really this part that we want to evaluate. And again, this is easy because our r here is just 1 over 16. And so obviously this is less than 1. So our result tells us this is 3/4, this right here, times 1 over 1 minus r, which is 1 over 16. And now I just have to do a little bit of algebra here, or a little bit of arithmetic, really, right? 3 over 4 times 1 over, and I'm going to get here 15 over 16, right? And I'm going to flip that. So I'll have 3/4 times 16 over 15. And I end up getting 4/5. And that's my final answer. So even though this was not a geometric series, I was able to manipulate it into such a form that its final expression could be written in terms of a geometric series that I can then easily evaluate. Now, why does this work? So I showed you this in class, and I'll just mention this again. It's based on a nice little formula. So this is based on a nice little result that says 1 plus r squared plus dot 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 plus r to the n minus 1 plus r to the nth is equal to 1 minus r raised to the n plus 1 power over 1 minus r. And the reason why that's true, okay, and by the way, you should notice that this is the nth partial sum, right, for a geometric series, by the way. Okay. But I want to focus on just this statement right here. I want to show why this is true. And the reason why that's true is if I bring the 1 minus r over to the other side, I'm going to have 1 plus r squared plus dot 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 plus r to the n minus 1 plus r to the nth over 1 minus r. You notice that we actually get a telescoping sum. Okay. So if you look at all the terms that we have, initially I'm going to, when I go ahead and I multiply through by 1, okay, I'm just going to get back 1 plus r squared. Whoops. That should be r to the first, sorry. Okay. 1 plus r squared. So when I go ahead and I distribute the 1, I just get back this sum again, plus dot dot dot, r to the n minus 1 plus r to the n. And when I multiply through by minus r, the first term here becomes, well, minus r, right? So when I multiply minus r times 1, I get minus r. When I multiply minus r times the second term, right, I get minus r squared. And you can see that all the terms are going to be negative. And finally, when you get down to the end, this term will be minus r to the nth, and the last term will be minus r to the n plus 1. Right? And when you can add them, you see exactly what's going to happen. I'm going to have a telescoping sum here, right? These terms will cancel. These terms will cancel all the way down the line. And the only two remaining terms are this minus this. So this tells me that this formula is correct. Okay, so now that we've established this formula, what I want to note is that if r is less than 1, the limit of the partial sums is going to go to 1 over 1 minus r. So I'm going to note now that Sn is equal to 1 minus r to the n plus 1 over 1 minus r. Of course, I can split that up, right? 1 over 1 minus r minus r to the n plus 1 over 1 minus r. And what I want to do is I want to show that this is going to converge, right? So notice that I'm going to look at two different cases here, right? So if the absolute value of r is greater than or equal to 1, the limit as n goes to infinity of the partial sums is equal to 1 over 1 minus r minus 1 over 1 minus r, limit as n goes to infinity of r to the nth. And this does not go to 0 very clearly, right? This is not equal to 0. Why? Because the base is greater than 1. And when you raise a number greater than 1 to an increasing power, it diverges to positive infinity, right? This is an exponential function, actually. And so this is not equal to 0. So this tells me that it does not converge. And by the same token, when the absolute value of r is less than 1, this same limit, what's going to happen to this term? It's going to go to 0, right? So the limit as n goes to infinity of the partial sums. And again, when you're taking a number whose magnitude is less than 1 and you're raising it to an increasing power, its limit goes to 0. So this whole term will go to 0, and I get 1 over 1 minus r. Okay, and that's why the geometric series converges under these conditions, using this definition of what it means for a series to converge as the limit of its partial sums. Okay, we're going to work a lot of problems on these because we're going to find that geometric series are really useful and they occur a great deal.